We've reached the last of these of our little chats. There will be more example videos to come yet, so you'll still hear my voice, but this is the last of these explanation videos where you'll see my face. So I hope they've been useful, engaging, interesting, occasionally amusing, sometimes groan-inducing, but that you do feel more confident and comfortable to teach physics, that you really feel as though you do have a handle on the content and that you're ready to obviously go out and keep developing and learning your own understanding. So a little bit on radioactivity and elements. This also treads on the toes of chemistry a little bit, but we're interested in the nucleus, whereas the chemists are interested in the electrons. That's actually one way of distinguishing between the two. When it comes to atoms, physics is much more concerned with what happens right down in the nucleus. So in terms of radiation, the Curies, Marie actually was Polish and her original name was Skłodowska, and Pierre was French, and they married. They both worked on discovering radium and polonium. Polonium is named for Poland, Marie's home country, and they worked with Henri Becquerel as well, and Becquerel discovered radiation. This is one of those stories that may be a little bit apocryphal, but the notion was that he had a sample of radium and put it in his drawer, just wrapped up with some photographic film, and discovered later that the photographic film was fogged because the radiation had exposed the photo even though no light had gone near it. But certainly Becquerel discovered that these rays, that these elements were emitting some kind of ray that wasn't visible. So discovered radiation. The Curies didn't really know much about radiation when they were doing the work. Marie ended up dying of radiation poisoning and various ill effects of radiation. Pierre didn't, because he slipped and fell on a wet street in Paris and was run over by a horse-drawn cart. So the universe will get you one way or the other, but Marie was exposed to a huge amount of radiation, because the way that they actually isolated radium was to get several tons of pitch blende, which is an ore containing this radioactive material, and then in the laboratory successively reduce it down until you had the pure element. So they spent a lot of time around radioactive elements, not taking precautions on wearing lead aprons and big suits and so on like we would these days. Becquerel and the Curies got the 1903 Physics Nobel Prize, and then Marie later on got the 1911 Chemistry Nobel Prize as well. And there are only two people who have got Nobel Prizes in two different fields. Linus Pauling, I believe, has one in chemistry and one in medicine, and Marie Curie has one in chemistry and one in physics. So really an amazing achievement. I suspect there might be some revision in this, but atoms of a particular element have a particular number of protons. That's what makes them that atom. So carbon has 6, nitrogen has 7, and so on. Hydrogen has 1. So the number of protons is what makes them that particular element, and they can have a different number of neutrons. So helium, for example, typically has 2 protons and 2 neutrons, making its overall nucleon number. The nucleon number is just the total number of things in the nucleus. We used to call it mass number, but that's not a particularly good term. So nucleon number is the current SI term. So typically helium is 2He4, so 2 protons, 4 nucleons. But it also has a 2He3 isotope, which is 2 protons and only 1 neutron. So elements generally have an isotope has a different number of neutrons. Carbon always has 6 protons, which is what makes it carbon, but it can have 6 neutrons, which means the overall nucleon number is 12, and that's the most typical. Most carbon that we encounter has the 6 neutrons to make it carbon-12. Carbon-13 has 7, carbon-14 has 8 neutrons. Carbon-14 is a radioactive isotope of carbon, and we'll talk about that and its use in radiocarbon dating a little bit later. Uranium has 2 main isotopes, U-235. Uranium is element number 92. U-235 has a total nucleon number of 235. I can't do the maths in my head to subtract 92 from that, but that would tell you the number of neutrons. Uranium's most common isotope, though, is U-238, which has 3 more neutrons than U-235. 235 is the one that can undergo nuclear fission, which we'll talk about later. 238 doesn't undergo fission. So when you're enriching uranium, you're going from, I believe the naturally occurring ratio is about 0.3% 235 to 99.7% U238. You have to enrich it up to about 3 or 4% U235 for a nuclear reactor, and you have to enrich it to much more than that for a nuclear weapon. I could go off in a whole rant about the Iranian nuclear weapons or nuclear energy program and why it's not a nuclear weapons program, but that's probably a rant for another day. But it's interesting to think about. This is a periodic table that shows the stable elements and the radioactive elements. The light blue ones are the stable ones, and you'll see that most of the small elements near the top of the periodic table are stable. The light green ones still have very long half-lives. They're pretty close to stable. Their half-lives are on the order of over 4 million years, but not infinite or not longer than the age of the universe. So they're still considered to be radioactive. So you can see technetium, element number 43, the green one in the middle there, has one half-life, somewhere over 4 million years. It has one radioactive isotope. Bismuth you can see, and there are a few others. Down on the very bottom row you can see uranium, element number 92, neptunium 93, plutonium 94. Man, I should know what CM is. Californium. Interestingly, along that bottom row, the Americans got to name a lot of them because they discovered a lot of them, or because it was during the Cold War and there were American names and Russian names, and the American names have ended up prevailing. So actually, thorium, named after the god of thunder, Thor, protactinium. But you get, after plutonium 94, you get 95 americium for America, 96 californium, 97 Berkeley for the University of California at Berkeley, berkelium, and so on. 99 is Einsteinium after Albert Einstein. 100 is fermium after Enrico Fermi. 101 is Mendelevium after Dmitry Mendeleev, who actually discovered the periodic table in the first place, and so on. So nobelium is 102, lawrencium is 103. So you can see those names are relating initially to America and then to the history of atomic investigation and the scientists that were influential. So you can see the red and orange, the yellow, orange and red is in order of increasing radioactivity, which means decreasing half-life. They decay more quickly and therefore more viciously, more fiercely. They're emitting more radiation. And the purple ones are the really radioactive things, which have a half-life on the order of minutes, seconds, microseconds, nanoseconds. They are not known in nature. They are made by humans in particle accelerators, and they usually then decay again almost instantly. So we create them an atom at a time rather than a kilogram at a time. And so those are much less known because they're really difficult to make, and then they don't hang around long enough for us to do measurements on them. So some sense of the isotopes and the elements. So radioactive decay. Decay has two main forms, but there are heaps. The radioactive decay article on Wikipedia actually has a really nice table of the various kinds. But beta decay is a beta particle is an electron that comes out of the nucleus, and we'll talk about why and how that happens. There's also beta plus decay, which is a positron, a positively charged anti-electron coming out of the nucleus. We're just going to talk about the ordinary old kind of electrons. So these are not electrons from the electron shells, the orbits. These are coming from inside the nucleus and out with high energy. And alpha decay, which is a helium nucleus, 2 neutrons, 2 protons, coming out of the nucleus. Decays also emit energy. There is mass lost, and you remember E equals mc squared, so there is a mass defect. There is energy lost when these, there are energy lost to the outside environment when atoms form, and so when they break down by decay or by fission, energy is released back to the atmosphere. Some of the mass turns into energy and is released, and that's released in the form of gamma rays. So that's a radiation that comes off radioactive materials. I think I mentioned already, decay is probabilistic. Last week in relation to Schrodinger's cat. We can't know when a particular particle will decay. It's a random process. But if we have a large number of particles, then we can do statistics on how many out of those will decay given a given time. We won't know which individual ones are going to decay, but we'll know that half of them will decay in a certain amount of time called the half-life. So alpha decay, as I mentioned, is this helium nucleus, this 2 protons, 2 neutrons, so 4 nucleons overall. So that's an example. So radium, Ra, element number 88, has 222 nucleons. It emits an alpha particle plus energy. We haven't included the gamma ray in this equation, and turns into radon, which is a gas. It's sometimes found in the basements of places with rock basements and can be quite nasty for people living in those houses. So alpha decay is a relationship, and you can see if you actually just do the maths across the bottom there, you go 88 minus 2 is 86, so the number of protons has decreased by 2, or is consistent, it's conserved across there, and 222 minus 4 is 218. So things are conserved in these reactions. Beta decay occurs when a neutron decays. So a neutron is 0 charge overall, decays to produce an electron, which is -1 charge, and a proton, which is +1 charge. So we still have 0 charge overall. It's conserved. This will increase the atomic number, and we'll look at an example in a minute. But so a beta decay actually is a way of increasing the atomic number, the number of protons, and an alpha decay is a way of decreasing the atomic number by 2. Radioactive decay is measured in becquerel after Henri Becquerel, who worked on the discovery of radiation. 1 becquerel is 1 decay per second. There was an older unit called the Curie, which is defined as something like 3 × 10⁷ becquerel. But becquerel is the correct SI unit, and it's the one that we should be using these days. The activity A of a sample is given by the rate of change of the number of atoms of that material, N, capital N, with respect to time, or minus lambda times N, where lambda is a decay constant. A number of places use the minus sign before the delta N over delta T instead of before the lambda N. And it's a matter of definition of what you're using, the way that you're using that decay constant as positive or negative. We'll see in an example a little bit later that it's really, if you kind of keep in mind what's happening with the numbers, where they're getting bigger, where they're getting smaller, the signs are less important. But I just wanted to alert you to the fact that this is the convention that the syllabus uses. In the syllabus, in the depth of treatment document, they use this exact equation where the minus sign is in front of the lambda. But if you look at some other physics textbooks and sources, you will find it the other way around. So we can't predict when a particular one will decay, but we've got this equation for the rate at which a large sample will decay. Nt is the number of atoms of something at time t. N0 is the number at time 0. So we started off with 7 million atoms of it at time 0. How many atoms will we have at time t? Time at 0 times e to the minus lambda, the decay constant, times t, the time. Half-life is the time for half of a sample to decay, and you've probably run into this term before. Some materials have a half-life of nanoseconds. I mentioned the very, very radioactive human-made elements earlier that have very, very short half-lives. Others have half-lives longer than the age of the universe. So we could say that they are stable, but they are notionally radioactive. The thing is, though, remember that because it's a random process, you could have something whose half-life is greater than the age of the universe, but you would still see a decay every now and then out of a large sample of it because it's a random process. And one of the decays could happen right now. It's just that half of them won't have decayed by the, in 20 billion years or whatever it happens to be. For carbon-14, that isotope that we talk about quite a lot, the half-life is 5,730 years. So we know that quite well. So if I have a sample of 1 kilogram of carbon-14, I'll have half as much in 5,730 years, half a kilogram. In another 5,730 years, I'll have a quarter of the original amount, half as much as I had after one half-life. And it'll keep halving every half-life until it's of negligible amount. The half-life is related to the decay constant by this expression. Half-life equals log of 2, natural log of 2 divided by the decay constant. Now the natural log of 2 is just 0.693 if we round it. Why the natural log of 2? Because we're talking about half, so half the amount of time. So it relates to that and it's defined by that. So if you've got the half-life, you can figure out the decay constant by rearranging this formula, or vice versa. So carbon-14, it's formed in the upper atmosphere by cosmic rays hitting gases in the upper atmosphere or carbon dioxide in the upper atmosphere, creating carbon-14. Then it mixes into the atmosphere. It's taken up by plants as they photosynthesize, turned into sugar and food in plants. It's breathed in by us. It's breathed in by animals. So anything living has a certain amount of carbon-14 in it. Mostly carbon-12, but some tiny fraction of carbon-14. As long as you stay alive, that stays in equilibrium, because there's a certain amount in the universe, there's a certain amount that you're consuming, and it stays in equilibrium. You continue absorbing new carbon-14. As soon as you die, you're no longer breathing, eating, etc. You're no longer adding new carbon-14. So the carbon-14 starts decaying over time. So we can tell the decay of the carbon-14. We can use it to tell how long ago you died. We can only use it on living things, on formerly living things, and we can only use it up to a certain number of half-lives, because otherwise there's not enough left behind. So here's the beta decay. Carbon-14, if PowerPoint was less of a pain about subscripts and superscripts, I would have 6 at the bottom and 14 at the top. Carbon, element number 6, has 6 protons. Nitrogen, element number 7, has 7 protons, so I would have 7 nitrogen 14. They both have the same number of nucleons, but what's happened is one of the neutrons has turned into a proton and emitted an electron. So that E- there is an electron. That's a beta particle going out. The little V shape, and again, if I had a Greek alphabet, that's actually nu, because it's a neutrino. It's an electron anti-neutrino, actually. And so a neutrino is part of quantum. It maintains the spin and number of quarks and various other qualities of the various particles involved. But we don't need to worry too much about those at high school level. But and there'll also be some energy when this decay happens. So here's an example of a calculation of a radioactive decay, how long something has been around. So we know that the sample originally contained 270 grams of carbon-14, and now it contains 12.3 grams. So it's obviously decayed a lot. Sorry, I meant to mention, decay sounds like, rotting flesh or whatever. It's obviously a completely different process, but we use the same word for the decrease. It's not that the atoms get old and moldy and go off and decay. It's that they break down in accordance with these physical laws and these random processes. So we were given the half-life of carbon-14 as 5,730 years. I want to use the decay constant, so I have to rearrange that decay constant formula. T1/2 equals 0.693 over lambda, rearranging to make lambda the subject. Lambda equals 0.693 over T1/2. So the decay constant for carbon-14 is 0.00012. That's my decay constant. Then I'm going to use my n equals n0 e to the minus lambda t. 270 equals 12.3, so the number of particles we've got now and the number of particles that we had initially. Now, I've done a little bit of a cheat there. The fact that Avogadro's number relates the number of particles to a mole, and the atomic mass relates the number of moles to a gram. So we can actually use mass as a proxy for number of particles, and that's what I've done there. I've used 270 grams rather than 270 divided by 12 to get the number of moles times Avogadro's number to get the number of individual particles. because it appears on both sides of the equation. So all of those calculations would cancel out anyway. So I'm just going to use grams. So 270 equals 12.3 times e to the that. Take the natural log of both sides because we've got e to something and we want to get rid of that. So natural log of 270 equals natural log of 12.3. And remember, when things are multiplied and then you take the log, you add them instead. So testing your maths knowledge of whether you remember. So we've got 12.3 times e to the that. So now it'll be log of 12.3 plus e to the that. Oh, sorry, not e to the that, just that, because we've used the log of the e to the, we just cancelled out the e to the power. If I rearrange that around, and I actually lost a negative sign in there somewhere because the negative sign wasn't helpful in this instance. And that's, again, why that convention of where the negative signs go is a little bit of a thing. We get 25,740 years. So that's about 4-ish. If you do 4 times 5,730 half-lives, and we've gone from 270 grams down to about 12.3 grams. So we've gone down by a factor of about 2 to the 4, which is what? 2 squared is 4, 2 to the 8 is 6, 2 to the 3 is 8, 2 to the 4 is 16. So we've divided by about 16. Yeah, to the extent that I can do it in my head, that's about right. And it's not precise, but we've actually calculated how old our sample of formerly living matter was when it died, based on this carbon dating. I mentioned before, can only be used on formerly living things about 50,000 years, depending on how big your sample is. Because 50,000 years is about 8 half-lives. And that means 2 to the 8, which is quite a tiny proportion of what you originally had will remain. So that's why there's that limit, because usually you're working with quite tiny samples of archaeologically important substances, and you're trying to not destroy your sample with your testing. So anything over much over about 50,000 years, we're not using carbon dating for. We're using some other kind of radioactive dating. There is rubidium, strontium dating. There is rubidium dating. There is a whole variety of different isotopes that have half-lives on the order of millions of years that we can use to date rocks that are millions or billions of years old. So we use those methods. The method's the same. You figure out how much was there initially, how much is there finally. Usually by knowing that, you saw that the radium decayed into radon. The radon itself is radioactive and will decay into something else. But at some point there'll be a stable isotope. So you can figure out the ratio of what the thing decays into to the ratio of the thing itself to know how much there was initially and how much there is finally, and figure out how old something is. So that's one of the important uses of radioactivity. Another one is nuclear energy. So fission and fusion are the two main kinds of nuclear energy that we use. Fission occurs when you have a big nucleus and it splits apart, usually because it's been hit by a neutron. Now, I could talk a bit more about nuclear power stations and moderators and why they're needed to slow the neutrons down that come out and so on, and chain reactions, but I don't think we really have time here, and it's not really on the syllabus. So it's certainly something you could do for an extended response task, get students to research that and be interested in nuclear, hopefully not build one in their shed like a kid did in the US. So a neutron comes in. You can see uranium-235 in this case, which is a fissile, fissionable isotope. Neutron comes in, 1N, and then it splits into a barium and a krypton. So we've got 139 barium and 94 krypton, and 3 neutrons go out. Now the fact that 3 neutrons go out and when 1 came in mean you can get a chain reaction, because those 3 neutrons going out can collide with other U-235 nuclei and cause them to go off. And this is how you can get a nuclear explosion, because one nucleus isn't going to cause an explosion. But this chain reaction, this growing chain reaction, because it's 1 to 3, can cause it to then explode. In a nuclear power station, you don't want it to explode. So what you want to do is have control rods that absorb 2 of the 3. so that only one of the three creates a new. So you've got a stable reaction, 1 to 1 to 1 to 1 to 1 continuing, and the other two neutrons are taken out of the system. In a weapon, you want this rapid chain reaction. Fusion, on the other hand, occurs when two small nuclei collide and form a large nucleus. So in this case, I've got two hydrogen nuclei, but different isotopes. Hydrogen is normally 1H1. It's just one proton, and its nucleon number there is just the one. But it can have a neutron. If it has one neutron, it's H2, which is called deuterium. And if it has two neutrons, it's called H3, tritium. So deuterium and tritium, two isotopes of hydrogen, if they collide, you can get a helium, 2He4, and a neutron released, and energy released, lots of energy released in a nuclear reaction. So fusion is the reaction that powers the sun and all the stars. Fission we use in nuclear power stations. Both we use in weapons. Most of our nuclear weapons that have been used, well, the two nuclear weapons that have been used in warfare against human targets were fission weapons. After that, fusion weapons were developed. The hydrogen bomb is a fusion weapon. But what it actually does, because to get fusion going, you require very high amounts of energy. What it actually does is fire off a fission bomb and use that to fire off the fusion reaction with the hydrogen, and that makes a much bigger bomb again. So the hydrogen bomb is a fusion bomb with a fission bomb just used as the fuse, effectively, for that. Why both combining small nuclei and ripping apart big nuclei will release energy relates to the binding energy per nucleon graph. But again, that's probably a little bit beyond what we've got time to go into here. But it turns out that for small numbers of nucleons, bringing more together releases energy. It increases the binding energy, the lost energy in the nucleus, and releases energy. And for large things bigger than about iron is about at the peak of the curve, and iron therefore is a very, very, very stable element. And then as you go further down the curve, you get into the radioactive elements, and it turns out that breaking those big ones apart will bring you back towards the peak and also release energy. So going towards the peak of the binding energy per nucleon curve from either direction releases energy.